screen space curvature for production quality rendering and compositing. Curvature is commonly employed for enhancing details in textured 3D models, or to modulate shading at the rendering or compositing stage. However, existing methods that compute curvature in object space rely on mesh-based surfaces and work at the vertex level. Consequently, they are not well adapted to production quality models that rely on either subdivision surfaces with displacement and bed maps, or on implicit and procedural representations. In practice, they would require a view-dependent scene discretization at each frame to adapt geometry to visible details and avoid aliasing artifacts. Our approach is independent of both scene complexity and the choice of surface representations, since it computes mean curvature from scratch at each frame in screen space. It works without any preprocess and provides a controllable screen space scale parameter, which makes it ideal for production requirements, either during rendering or compositing. We take inspiration from methods that reconstruct surfaces from point clouds equipped with normals, starting with a 2D example. Curvature is computed at each point of a 2D point cloud by fitting a circle to a neighborhood of sample points. Scale is adjusted by changing the size of the neighborhood considered for fitting. The same approach, when applied to 3D data, yields a sphere from which mean curvature is easily extracted. Here, we display curvature with a color code, with concavities in red and convexities in blue. Note that curvature is tied to the initial pose and thus does not vary when we zoom in or out. This object space solution will lead to aliasing artifacts when objects are seen from a distance. In our approach, we collect surface samples in a prescribed screen space neighborhood, hence constructing a local 3D point cloud. The curvature computed from the local point cloud is a close approximation of object space curvature, as long as we clip neighborhoods at occluding contours. With this approach, objects exhibit less details when they get farther from the camera. This automatic simplification reduces aliasing artifacts. By controlling the size of the neighborhood, the user is also able to select the scale of details captured by curvature estimation. It also outputs two additional parameters: a smooth normal vector and an offset value that measures the amount of local relief. A benefit of our approach is that it works naturally with ray tracing. We have implemented screen space curvature on top of the ray tracing engine of Modo, which provides for interactive previews. Compared to bitmap images, the only difference is that we send additional rays to compute the screen space neighborhood. This amounts to negligible overhead in terms of performance compared to subsequent rendering operations. In this scene, a character model with subdivision surfaces is rigged to display a matte green. Our mean curvature is used to alter the color pass on the face, and our offset parameter is used to modulate shading on the dress. This scene shows another example, with a procedural displacement generated at render time. Our mean curvature is computed after the displacement pass. In the near future, we plan to use screen space curvature to ease the perception of shape during sculpting, directly in viewport. We also plan to use it to drive NPR shaders, so that lines and color regions dynamically align with salient surface features.